Hello students, in this lecture and in the next lecture we will study the chapter 6 from the EEE microcontroller and embedded systems, our standard textbook by the author Mazidi, which is the advanced assembly programming. The topics in this chapter are: first we will see some assembler directives, then we will study addressing modes, and finally, we will see some miscellaneous topics such as how to use the EEPROM and what is a macro. So let's start. You already are familiar with the similar directives .equ and .org. We know that the directives made the coding easier, and plus they also help us to make the code look more understandable and readable. So it is a good practice that the code that we write is readable and understandable for any person if we want to share our code with. Because if we do not take care that our code is readable and understandable, and if we revisit our own code after some time, we will find it difficult to understand the code written by us. So you are familiar with .equ. We are naming a constant value 50. We are giving it a name alpha. The assembler at Mega, the AVR assembler also supports arithmetic and logical operations on the immediate values. So this must be clear that all these operations are performed while the code is being assembled, and they are not performed at the runtime. It means that when the code is written to the code memory of the ATmega controller after assembling, here the value is already computed. So the examples are: we are subtracting two constants, multiplying and adding a constant value, we are performing logical operations, we are performing the shift operation here. So let's see how they make our code more neat and clean and understandable. Here the task is to set the Z register, the zero flag of the status register. We know that there is a status register which lies in the special purpose register, special function register range, which has flags which set as a result of operation, and we can also set them manually by writing any value to it. Here we want to set the Z flag. So without using the directive, we know that the Z flag is flag number 1, bit number 1, which means if we just need to set the Z flag, we can write 0x02, because 0x02 is here, Z flag is set. So that if we write it that way, we can see that anyone who is also familiar with the hexadecimal notation, he will also require some time to understand which bit is being set, and let alone anyone who is not that familiar with the hexadecimal format. But if we write using the directives one left shifted sreg times, we know that we have just seen in the previous slides that we can perform logical operation, shift operation. One left shifted sreg time means sreg z times means one left shifted 1 times. If you shift one by 1 times, which if you have 1 here and you left shift it by 1 times, you will get 2. So it's the same end result, but it is easy to understand. So 1 left shifted SREC times and we out. Similarly, if you want to set multiple flags, just like you want to set V and S flag, V flag is bit number 3, S flag is bit number 4, V flag and S flag, yes, if you want to. So here again, if we don't use the directives, and we will write it as, here are the 8 bits and we have to check bit number V and S, which are 0, 1, 2, 3 bit and S, which means 0x18. So without assembler directive, we will write LDIR16 0x18. We can again clearly see that writing in this way, you will have to think a few seconds to realize which bits are being set. But if we use the assembler directive, here we have used 1 left shifted SREC V times and 1 left shifted SREC S times. So 1 if and SREC V is defined as bit number 3, is its value is 3, and SREC S is defined as 4. 1 left shifted 3 times will set this bit. 1 left shifted SREC 4 times will set this bit separately. So you'll get 2 bytes in which in 1 byte bit number 3 is set and then the other one bit number 4 is set. And when you perform the OR operation, you get the same result, which is hexadecimal 18. In a byte, both bit number 3 and 4 are set. So we have seen that this makes our code more easy to understand. So again, in another example, we'll see 2-3 examples regarding the same concept. Write codes to set port B2, port B4 of port B21 and clear the other pins. Port B2 and port B4 means 0, 1, 2, 3 and 4, which is 0x. If we set this one bit and this one, you get hexadecimal 14, which is again a dull way and takes time to understand. And binary, we already have written it is hexadecimal 14 here. With the directives, we can write 1 left shifted 4 times, 1 left shifted 2 times. It will give us 2 bytes which have here bit number 2 is set and here separately bit number 4 is set. Then we performed the OR operation in between them, which gave the same result. Finally, we got the byte where the 2 bits are set. We can further make it more clear by replacing the constant values with their names. We can use the EQU directive and we can name port B4 is equal to 4 and port B again EQU directive here, and port B2 is equal to 2, and we can replace 4 and 2 with their names, port B4 and port B2. So 1 or 2 more example before going to the next directive. Here we are asked, what is the result of assembling the following program? What is the value in R20? C1, we named the values 2 to C1 and 3 to C2, and here we are performing OR operation between value 2 and 1 left shifted 3 times. 1 left shifted 3 times will give us 8. 1 left shifted because 0, 0, 0, 0, 0, 0, 1. If we left shift it 1 times, this bit is set, 2 times and 3 times. If we left shift it 3 times, we get 0x08. So one byte containing 8 and other byte we have directly written C1, which is 2 here. 2 OR operation with 8 will give a final byte where bit number 2 and bit number 4 are set. So in hexadecimal we can write it as 0x0A. So R20 will get this value. Yet another example. Here you can note that another directive .include is used to include a file m32def.inc. You will find such files for all the different variants of the ATmega32 microcontroller. The one we are using is ATmega328P, so you will also find 328P def.inc. This include file contains the list of all the declarations where the constants are named with their names. Ports have their addresses, and the file contains the name. For example, port D has some address, so we named port D constant. We gave the address some name, so that in the code it is more convenient. We do not need to memorize the address, and it is more understandable. We use the name. So in the same file, all the pins are also named. The file here will contain .equ pb4 is equal to 4, and similarly pb2 is equal to 2. So if we don't include this file, here we need to write the address of this register, direction register of the port, and here we have to write the values 4 and 2. But since we included this file, we wrote here pb4 and pb2. So 1 left shifted pb4 times is 1 left shifted 4 times, and 1 left shifted pb2 times mean 1 left shifted 2 times. So 1 left shifted 4 times will give 0x10, and 1 left shifted 2 times will give 0000 0x04, and if we combine them, we perform OR operation between them, we will get 0x14. So TTRB will get 0x14, which means that pin number 4 and pin number 2, they are set to be as output pins. The next directive before we go to the addressing mode is assembler directive high and low functions. The high and low functions, there are situations where we need to load 16-bit data into microcontroller registers. The one common situation is where we have separate register SPH and SPL, which are the high and low registers for the stack pointer. So the combined make a 16-bit register. And the stack pointer, you might have studied, it should be initialized to the end of the memory location. So without directive, first you need to see what is the end address of your variant of the microcontroller. Then you need to divide that into the lower byte and the higher byte, and separately load SPH with the higher byte and SPL with the lower byte. The include file just discussed add mega 3 to the 328.include 328p def.in. For all the variants, different variants, it also defines the end address, the last address of SRAM with the variable RAM end. So using the high and low directive, we will also see that this directive can be used in more situations, but the more common situation that we encounter is when we initialize the stack. So the include file already contains the 16-bit value RAM end. So the convenient and neat and more understandable way is by using the high and low functions. These are the assembler directives. High RAM end will give the higher byte of the 16-bit data, and low directive of any, here you can place any 16-bit value or constant. You can directly write, like in this way, you've directly written a 16-bit value. So it will give the lower byte of the 16-bit value, which can be later shifted into the register. So let's go to the addressing mode. Addressing modes refer to that how operands are specified in an operation. There are multiple ways that we can supply operands in an instruction. As a single register, two register, directly memory addressing from the SRAM or the total memory range directly by giving the direct address of the location. Let's see all these one by one. So the first one is a single register. The operand is a single register. We will see two type of variants. One, these instruction where there is no immediate value, just a single register. Negate all the contents of our routine, complement the content, increment. These are very commonly used in the loops. Increment a counter, decrement a counter, or date write. If we see the assembly code, it has, you know that the instructions of that mega, they are either 16-bit wide or 32-bit wide. So this is a 16-bit instruction. It has opcode and just one part here, a 4-bit specifying the register. Since the bits allocated for register are 4, so it means you can only use 16 register in it. But if you look at the data sheet of the ATmega 328P, which is the microcontroller in the Arduino Nano board, there you have 5 bits allocated, so you can use all the 32 register in this instruction. The second type containing single register are the one which have one immediate value, such as LDI, loading and immediate value. Immediate subtraction, subtracting immediate value from a register and storing back to the same register. And a logical operation and operation and I. Here, if you look at the opcode, you have obviously in all the instructions, in the machine code you will have opcode that specifies the type of operation. You have 8-bit immediate value, which means the immediate value either loaded into the register or performing the subtraction operation, it is at max 8-bit. So maximum value that can be loaded is 255 decimal. So you cannot go on writing LDI any register and you write here 1000 and we already, because the limitation is the registers are also 8-bit. So the value immediate loaded is 8-bit. And for the register, you have 4-bit allocated, so which means 2 raised to power 4 is 16. You can only specify 16 register. That is why these instructions only work for register R16 to R31. two register addressing mode. The common arithmetic instructions here, the both of the operands are registered, and in the opcode you can see that the bits allocated for registers are for each source. Both of them are source, and one of them is also the destination as well as the source. So both have 5 bits allocated, so these instructions can work on all the 32 registers. Direct addressing mode. In the direct addressing mode, we move the value from the data RAM to the register by specifying the address of the location, specifying directly the address. We have two variants that use the direct addressing mode. One is LDS STS and the second one is in out. LDS and STS, they are 4-byte instruction. In the next slide, I shared the opcode or the machine code for LDS and the in out instruction. As you can see that the LDS and STS, they have 32-bit machine code, and in out have 16-bit machine code. So since they have the large machine code, they have 16 bits allocated to specify the address, which means that they can work for all the data memory range. They have 16 bits. These instructions work for the complete memory range. So you can shift the data from the complete memory range, which includes GPR, special function register, and SRAM, into the general purpose register using LDS and STS. Whereas for the in out instruction, they also move data between data RAM and the data memory and the general purpose register, but their source for the in instruction is limited to just the special function register, which means the IO ports, timers, and that is why these are 16-bit instruction. So why would someone prefer in and out? Because we have convenient in the microcontroller, we are supposed to take input from the surroundings, and if we use the general instruction LDS STS, they are 4 bytes instruction and they take 1 cycle more than the in out instruction. They take 2 locations of this code memory and they take just 1 location in and out. Other than that, the function is same. Moving data, LDS takes data from the location in the complete data memory range and moves it to the general purpose register. STS performs the opposite operation. It moves the data from the general purpose register to the complete memory range. You can also specify a register here, which means if you want to move the data between register 0 and register 1, you can write LDS R1 and 0 here. 0 is the address of the first register. What we need to take care of when we use these two instructions, one thing we need to consider is while we use the include file which was discussed earlier, in which the addresses are given names. For example, pin B, port B, pin B register has some address, port C register has some address. So these addresses are written specific to the in-out instruction and not for the LDS and STS instruction. So what is the difference between the two addresses? For the LDS instruction, which is applicable for the complete memory range, it uses the actual absolute address. For example, let's look at the table. Pin D has an absolute address of 30. Why there is an absolute address of 30? Because initially we have 32 registers, general purpose register. After that we get to the special function register. So the initial 32 offset is always added. So hexadecimal 30, if I use the calculator to give you the decimal value. Hexadecimal 30 means 48. So it has absolute address of 48. But if we subtract from 48 the initial offset of 32, which is the addresses of initial 32 register, we get 16, which is hexadecimal 10. So its IO address is 10, whereas its absolute address without subtracting the offset is hexadecimal 30. The M32, the include file uses these addresses for the IO pins. So question here, let's solve this example before going to the next addressing mode. They write a code to send 55 hexadecimal to port B, and in 3 different ways: the register name, the IO address, the data memory address. And before going to the solution, we are clear here that when we use the IO address, we will use the out instruction, and when we use the data memory address, we will use the pair LDS-STR instruction from this pair. We'll use the STS instruction. So let's go. First one, we have to first we make all the pins of the port B output pins by writing FF2 into it. So port B is now output pin, floated value 55 into register, and use the out command to write the value to port B. And again, if you use the addresses, we have to look at the table for the particular address, or you can also open the include file to see the address, or you can download the data sheet of the processor and you can look at the address. (0x17) is the IO address of data register B. Here since we haven't used the include file, we have to use the address here, the IO address, when using the out. Similarly, we have used the IO address of port B. We haven't used the include file, that is why we have written the address here. When the same task is done using the LDS, STS and STS instruction, you can see that the address is changed because now the offset 32, which is hexadecimal 20 is added. That is why 17 is converted into 37 and 18 is converted into 38. Next addressing mode is register indirect addressing mode. The direct addressing mode has one disadvantage. If we want to read an array or write an array, we cannot do it with the direct addressing mode in a loop. If, for example, if you want to read 10, 100 elements of an array, 50 and even 20, 30 elements of array, we will need to specify or writing the address. Let's say in this example, if you want to write in the SRAM an array of 20, 30 elements, we have to specify each address one by one. 37, let's say SRAM starts with 100 hexadecimal, we will have to specify 100, 101, 100, each address manually one by one. We cannot increment a constant. We can only increment a register. So the solution is we have another type of addressing mode, which is a register indirect addressing mode. Here, the address from where we need to read or to where we need to write is inside a register. So that is why we can conveniently use it with arrays. There is one more complication with it. We note that the data memory address bus is 16-bit. So the address that we need to write in a register must also be 16-bit. And we have all the registers 8-bit wide. So what is the solution for that? The solution is there are 6 registers at the end of all the register from register R26 to R31 that can be used as 3 16-bit registers. They are named RX, RY, and RZ. For RX, its lower byte is in R26 and its higher byte is in R27. For RY, lower byte is in R28 and higher byte is R29 and so on. So can we load value in, do we have an instruction LDI RX? No, we cannot load a 16-bit value because we do not have, same is the problem again, we don't have a 16-bit register. So in order to load value, we will use the same same solution that we did for the stack pointer. We separately loaded SPL and SPH. Similarly, in order to load 16-bit value into RX, RY, or RZ, you will need to separately load the lower byte in R26 and higher byte in R27. Here you can again use the high and low functions, the assembler directives that are provided to separate the 16-bit address to 8-bit addresses. Here again in the diagram shown, X register has XL and XH, R26, R27, and so on. They can also be named XL and XH. So we needed to write in the location 16-bit address 0x130, which is 0x01 and 30, lower byte and higher byte. We loaded XL with the lower byte and XI with the XH with the higher byte, and now X register contains a 16-bit address. We can use the load instruction, which is the indirect instruction, indirect register, indirect addressing instruction, and the store instruction. These are the 2 instructions for the indirect addressing. We can load from the X a 8-bit value into register. Notice that the address is 16-bit because the address bus is 16-bit, but the memory is organized as byte. On each location we have a byte. Similarly, we can store from X into a register. So here we have an example comparison how these 2 instructions make reading or writing an array easier. The program, we have to write a program to copy the value 55 into memory location starting from hexadecimal 140 to 144. With the STS direct addressing instruction, you have to specify each address one by one, 140. Then you have 141, 142, 143, 144. By using the indirect addressing mode, we have loaded the address is 140. If we write the complete 16-bit address, it is 0140. So lower byte is loaded into YL and higher byte is loaded into the YH. You could have used .equ operator to write the address here 0x0140, and here you could have written low of address and high of address. So in the loop we write the value to the address. Y contains the address we just loaded. We're writing the R20 value, which is 55. We increment the address. This is the facility which is not available in STS. We can increment the register which contains the address. Here counter is decremented, and if it is not equal to 0, the 0 flag is not set. It is initialized by 5, so the loop will run 5 times. So we'll copy 5 values in a loop, and we can understand that if there were 50 or 100 values, how difficult would it be to write it using just the STS instructions. So register, there are many variants available of the register indirect addressing mode. And for the specific variant, if it is available in the microcontroller we are using, we need to see the instruction set data sheet to know which are supported by the version we are using. So there is one complexity which is solved by these variants, that since the register RX, RY and RZ, they comprise of 2 separate registers. Let's say if I consider RX, we have 2 separate registers, R26 and R27. And if there comes a point where R26 by incrementing reaches a state where it is 0xFF, and incrementing it further will make it 0x00, and there should be a carry to R27. But since they are 2 separate registers, the carry is not forwarded to R27. So this way, let's say, actually if here it is 0x01 and here we reach 0xFF, so after one more increment it will become 0x00, and R27 should become 0x00x02, but that won't happen. There is one other way to, without using the variant, to do that, but we will, since we have the facility to do, there are already instruction load data RNX plus. So these variants take care of this complexity, and you do not need to worry about that. The variant we studied, X stays the same, but if you use X plus, after loading location pointed to by X, the X is incremented. The X as a whole is incremented. So if there is a carry from the lower byte to the higher byte, it is transferred. Similarly, we have minus X, minus Y, Y plus minus Y. Write a program to clear 16 memory locations. Another example for the register indirect addressing mode. Write a program with 16 starting at data memory address 60. So complete 16-bit address is 0060. Lower byte loaded to XL, higher byte loaded to XH, and we have to clear the 16 memory locations. That is why the counter is initialized by 16, which gets decremented, and we have BRNE. And this variant of store instruction we are using, writing R20, which was initialized by 0, so that we clear the location. We clear the location, and since it is X plus, the address is incremented. After we write it, the address is also incremented out. So the loop is executed 16 times. and address gets incremented because of X plus instruction, and all the 16 locations are cleared.